Thanks everyone. Today we're going to be fulfilling the topic boy or more and knowing why it's one of the powerful string matching algorithms. So you're probably thinking, how is it? Well, you're in a scenario where you're looking up for your name. I'll go look, for example, for Carlos Jose. My guy takes so long because he's using a naive brute force search technique. However, this process should be one of the fastest techniques or he'll be fired. Boy or more helps in this scenario because it's a space and time trade-off strategy. Trade-off strategy. Space and time trade-off strategy optimization involves choosing between using more memory for quicker results or less memory for a longer processing time, tailored to the specific needs of our problem or system. Well, we have the two approaches. Time optimization, which is the approach that uses less compression and faster decompression, and vice versa, which is the space optimized approach. Now, since we covered these topics, let's jump right into the Boyer-Moore. Well, Boyer-Moore is a powerful string matching algorithm that revolutionizes. Yeah, again, Boyer-Moore is a powerful string matching algorithm that revolutionizes text search by cleverly skipping characters based on professed. Boyer-Moore is a powerful string matching algorithm that revolutionizes. Boyer-Moore is a powerful string matching algorithm that revolutionizes text search by cleverly skipping characters based on pre-processed pattern insights. It optimizes efficiency. As we scan text left to right, the algorithm minimizes unnecessary comparisons significantly, enhancing performance in finding occurrences of a pattern within a given text. Let's start off with the bad character rule, which is an Boyer-Moore algorithm that helps us quickly skip unnecessary comparisons during pattern matching by pre-computing a bad character shift table. We efficiently adjust the pattern's position based on the last occurrence of the mismatched character. This smart shifting minimizes comparisons and enhances an algorithm's overall. Second, which is the good suffix rule. The good suffix rule optimizes the pattern shifts in the Boyer-Moore by using a pre-computed good suffix shift table. This rule strategically adjusts the pattern's position based on the matching suffixes during a mismatch, improving the efficiency of the algorithm. Well, then now we're gonna try to construct the batch shift table. This is a simple code that shows you the way of constructing it. This is of course Python. Shout out to W3 Schools for the code. We got the simple input, which is some random characters. I don't know how to read it, and even with the pattern, we're gonna use some random characters that eventually you should try to find in the input. And we're gonna build our table respectful to the letters. Of course, we don't repeat them, and that's the basic formula we're gonna go through with it. In constructing the batch shift table, we are going to use the formula there, which picks the max for being either 1 or the total length of the pattern subtracted by the index minus 1. And that's how it's gonna go on. That's 8, that's gonna be 7, 6, and then the G is gonna be overwritten, and the cycle just continues. And 9, which is any random character. In the bad shift table analysis, the first for loop in the bad character heuristic holds one for loop, which gives it the time and the time complexity of big O M. On the other hand, the search function, we have another for loop, which is now stated as a while loop, and the common that's the common operation, uh, which gives it a one, another one, gives it a big O n. In the search, it has another for loop, and the basic operation is the addition, which will add up one and gives a time of complexity of big O n. And when calculating the time complexity, we take the worst case for the bad shift table and sum it up with the search complexity, finding which one is the maximum, which gives the time complexity of big O n, where n is greater than m. In analyzing the good suffix table, we have two while loops, which gives us the time complexity of m times n, of big O m times n. And on the second case, we have one for loop, and that's the basic operation, which gives us a complexity of big O m. And the search, same wise as the first case, has two while loops, giving us time complexity of O m n. In calculating the good suffix time complexity, we take the good suffix first case, sum it up with the second case, and the third complexity, giving us the big O of mn complexity as the largest time complexity. Thank you everyone for listening.